Hello again and welcome back. I am Ian, and today's homework recap for the final exam for Structures 1 is prime factorization and prime numbers. This was actually a really fun one. I love prime factorization. It's one of my favorites. I love doing the trees, like the factor trees, which is what we're going to be doing for these first three problems. Oh, okay. Find the prime factorization of each of the following numbers by using a factor tree. So we're going to start with 75. And remember the way factor trees work is you try to get a number down to its prime factors. So if you have 12, for example, you can pick any factors you want, really. 12, I can do a couple different things for actually. 12, you can do 2 and 6 or 3 and 4. Say if we do 2 and 6, right? 2 is a prime factor. 6 is 3 and 2. And then you end up with 2 squared times 3. 3 and 4. 3 is a prime factor. 4 is 2 and 2. 2 squared times 3. Notice how it doesn't matter what I started with because I'm going to end up with the same answer anyway. That's the beauty of factor trees. It's kind of like creative freedom, like how the strip diagrams are. It's not too much creative freedom because there's only set numbers that can multiply to specific numbers, but I like to think of it as creative freedom. So, 75. We can break this up into a couple different things. I have decided when I did the homework back in the beginning of the semester, I decided to do 5 and 15 because 4 times 15 is 60. 5 times 15 is 75. 5 is actually a prime factor because nothing else can multiply to 5. It's just 1 and 5. 15 is not a prime factor. This can actually be broken up further into 5 and 3, which are both prime factors. So our final answer is 3 times 5 squared. It's 5 squared because there's two 5s, and everything's getting multiplied. Technically, this is the same as 3 times 5 times 5, but remember 5 times 5 is the same as 5 squared. So there are other things you could do for 75. 75, you could have did the 5 and 15, or you could have did 3 and 25, which would give you 3 as your prime factor, split up 25 to find your 5s. This way that I did, you find your 5, split up 15 to find your other 5 and your 3. But again, it doesn't matter which way you do it. You end up with a 3 and two 5s. You end up with the same answer. So, moving on to 350. This one, we can easily do 35 and 10. 35 can break further into 7 and 5, which are both prime factors. 10 into 2 and 5, which are also both prime factors. So we have a 2, we have two 5s, we have a 7. Remember to put them that they're being multiplied. It doesn't matter if you put it's technically better to put 5 squared, but if you don't remember that, you can put 2 times 5 times 5 times 7. Just make sure that they're all getting multiplied. Don't put 2 plus 5 plus 5 plus 7. That's wrong. That's not 350. That's 19. But yes, it's also better to put them in order, kind of some sort of order. I like to do least to greatest. It just kind of flows, progresses. But you can do any order you want. So also remember to box our answers. Okay, 60. We can do couple different things. We can do like 30 and 2, or 15 and 4, or 3 and 20. Or we can do, I like 12 and 5. 5 is a prime factor. 12 is 3 and 4. 3 is a prime factor. 4 is 2 and 2, which are both prime factors. But again, you can do any of these different ways to get to 60. Like 10 and 6. You can do 10 and 6. Break up 10, 2 and 5. Break up 6, 2 and 3. You still have two 2s, a 3, and a 5. And that's the beauty of factor trees. You can just really just do whatever you want to an extent, but you can really just do whatever you want. Use whatever numbers you want that still multiply to get that base number, and you're chilling. You're going to get the same answer if you do it right. So now, with number 2, we're going to use the prime factorization to determine if each of the following is a factor of each of the above numbers. Write the number it is a factor of and show the numbers used to make your decision. So we're actually going to use these prime factorizations from these numbers to see if these numbers are factors of any of these 3 numbers, if you're catching my drift. So we're going to start with 15. So looking at anything here, we can determine, oh, what happened? Oh, okay. A little hiccup there. The hiccup's still going on. All right, there we go. I fixed it. Okay, so using these numbers, so basically essentially we're looking at these prime factorizations to look and see if any of the numbers in any of these numbers are going to essentially multiply to this. So we're going to start with 15. We can take it number by number. So 75. Yeah, 15 is a factor. So we can write 75, and we know this because we have 3 and 5. 3 times 5 equals 15. Same with 60. 60, we also have a 3 and a 5. So 60, because 3 times 5 equals 15. That's the whole gist. So next up would be 14. Nothing out of 75 can make 14, because we have 3 times 5. So we have 3 and we have 5. We have 3 times 5 is 15. We have 5 times 5 equals 25. And we have 3 times 5 times 5, which equals 75. None of those numbers are 14. Same with 60. We have 2, 3, and 5. 2 times 2 is 4. 2 times 3 is 6. 2 times 5 is 10. 3 times 5 is 15. 2 times 2 times 3 is 12. 2 times 2 times 5 is 20. And then 2 times 2 times 3 times 5 is 60. But 350 has 2 and 7. 2 times 7 is 14. So 350, because 2 times 7 equals 14. Kaboom. Okay, next up is 12. So for 12, we're looking for like a 2 and a 6, or a 3 and a 4, or like anything else that can make those numbers. So again, 75 has no even numbers whatsoever. We're not getting anything out of there. 350 has a 2, but doesn't have a 6, doesn't have like a 3, nothing like that. Can't make 12 out of that. 60, you don't have a 4, but you have 2 times 2, which equals 4, times your 3. 2 times 2 times 3 equals 12. So, yes, 60. Oh, because 2 times 2 times 3 equals 12. Because 2 times 2 is 4. 4 times 3 equals 12. And then finally, 25. 25, we're really looking for 5 times 5. And we have it in two places. 75, we have 5 squared. 5 squared is 25. Same thing with 350. 5 squared is 25. 60, we don't have that. Nothing out of those prime factors can equal 25. Nothing made out of these numbers can equal 25. But we still have 75 because the 5 squared equals 25. And then 350 because, again, 5 squared equals 25. Finally, we have this problem. I feel like this has a very high chance of being like something on the exam. The only prime factors of a certain number, so we don't know the number, but we know this very specific number that we do not know has 2, 5, and 7 are the only prime factors. So it could be any combination of that. It could be 2 times 5 times 7. It could be 2 squared times 5 thirds times 7 to the 7th. Like, could be any of these combinations. It's just that the only prime factors are a 2, a 5, and a 7. Now, when we're given our answers, though, instead of given numbers, we're given expressions. You might be thinking, that's a little weird. However, we can still find our answer. And you might be thinking, okay, your first instinct, and I remember this was a lot of people's when I was looking around the room, like from sitting from my seat, this was a lot of people's first instinct was just straight up going to each like expression and multiplying it. So like 10 times 49, they're like, okay, so that's 490. And then try to like factor tree 490. That's a lot of work, man. Do not have to do that. Plus, some of these are like huge numbers, like 24 times 25. Guys, what are we doing? We don't have to do that. What we can do is find the prime factors of each of these factors. Because we already know this like random number is going to have 8 and 35 as factors. So we already know it's not a prime number. It's like 10 and 49, for example, like 490. How are you going to factor tree that? 10 and 49? Like, guys, why don't, instead of multiplying it together just to split it apart, excuse me, we can essentially just break down each number now and not multiply together just to split it apart. We just start splitting. So let's take A, for example. We have 8, which can split into 4 and 2, 2 and 2, and we have 35, which is 5 and 7. Our answer for A is 2/3 times 5 times 7. This is promising. This has only 2, 5, and 7. Take a quick look at B. We have 15, which can be 5 and 3, and then 9, which is 3 and 3. So we have 3 cubed times 5. I don't see a 2. I don't see a 7. I see a 3 also, so uh-oh. We have C, which is 10, which you can do 2 and 5, bang, bang, and 49, which is 7 and 7. So you have 2 times 5 times 7 squared. That's a 2, yep. And then finally, we have D. We have 24, which we can do 8 and 3, and 2 and 4, and 2 and 2. And then we have 25, which we can do 5 and 5. So this one's what? 2, ooh, I don't know what that was. 2 cubed plus, oh, not plus. Remember I said don't do that. Times 3 times 5 squared. Looking at these, we're looking for only 2, 5, and 7. So I see A has that. I see C has that. I see B does not have that. And I see D does not have that. And then you're asked to explain your thinking. So what I wrote was, instead of having to multiply each expression, you can find the prime factors of each number separately, which will end up being the same prime factors as like the number that you get if you multiplied each expression. So like, for example, the 10 times 49 is 490. 490's prime factors are still going to be 2, 5, and 7 squared. Doesn't matter if you multiply it and get 490 or just keep it 10 and 49, like split up. And yeah, that is it for this one. So just a recap for prime factorization and prime numbers. We reviewed how to do factor trees and like getting our prime factors from larger numbers through our factor trees. We were then able to use prime factorization to determine if each of these numbers were factors of these larger numbers based on using their prime factors. And then we had an unknown number, but we knew its prime factors, and we were given options, like from expressions, and we were able to determine which of these expressions could be the specific number that had prime factors of only 2, 5, and 7. And that is all for this homework. Thank you so much for watching, and happy studying.